March 30th, 2022. An astronomer named Brian Welsh is staring at a Hubble image of a galaxy cluster called WHL 0137-08. He's not looking at the cluster itself. He's looking at something behind it. A distant galaxy stretched and warped by gravity into a long arc. And then he sees it. A single pixel, flickering. Too bright for where it is. Not a galaxy. Not a cluster of stars. One star. One star from when the universe was 900 million years old. That should be impossible. Individual stars are too small, too faint to see across cosmic distances. We can barely resolve stars in nearby galaxies. Beyond a few 100 million light-years, stars blur together into galaxies. This star, if it really was a star, was 12.9 billion light-years away. Accounting for the expansion of space since its light left, it's now 28 billion light-years distant. Seeing one star at that distance is like spotting a candle flame in Tokyo from New York. Through fog, with your naked eye. Impossible. Unless the universe gave you a telescope. The galaxy cluster between us and that distant star weighs quadrillions of suns. Its gravity bends space-time so severely that it acts like a natural lens, magnifying whatever's behind it, in this case, by up to 10,000 times. And for a brief cosmic moment, the alignment was perfect. The star drifted behind a caustic, a region of extreme magnification. And we could see it. They named it Eärendil, Old English for morning star, the light of the dawn. And when the James Webb Space Telescope looked at it in 2023, it told us a story about the very first stars and what we're still getting wrong about the early universe. This is that story. In 1915, Albert Einstein published General Relativity. The radical idea, gravity isn't a force, it's geometry. Mass curves space-time. Objects moving through curved space follow curved paths. Light has no mass, but it travels through space-time, so massive objects can bend light's path. In 1919, during a solar eclipse, Arthur Eddington measured starlight bending around the sun. Einstein was right. But the real implications took decades to sink in. If a massive object bends light, it acts like a lens. And if you put that lens between you and a distant object, you get magnification. Galaxy clusters are the universe's heaviest lenses. Trillions of solar masses concentrated in one region. When a distant galaxy lies directly behind a cluster, its light gets bent into multiple images, sometimes a full ring called an Einstein ring. More often, distorted arcs, stretched around the cluster like taffy. But here's the key. Lensing doesn't just distort, it magnifies. The amount of magnification depends on alignment. Typical strong lensing, 10 to 50 times brighter. But there's a special case. You've seen caustics. They're the bright patterns at the bottom of a coffee cup when sunlight hits at the right angle. Light focused into curves. In gravitational lensing, caustics are curves in space where magnification goes extreme. Not 50 times, not 100 times, thousands. If a star drifts behind a caustic, it brightens dramatically for weeks or months as it crosses, then dims again as it moves away. This is called a lensing caustic transit. And that's what Eärendil did. In 2016, it was invisible. By 2019, detectable. In 2022, bright enough to identify as a single star. We caught it crossing the caustic. The universe gave us a window, and we looked. Normally, when we study distant galaxies, we see averaged light from billions of stars mixed together. Young blue stars, old red stars, dying giants, all blended into one spectrum. We can learn about the galaxy as a whole, its total mass, star formation rate, chemical composition, but we can't study individual stellar populations. It's like trying to understand an orchestra by listening from outside the concert hall. You hear the music, but you can't isolate the violins from the cellos. Eärendel let us isolate one instrument. When you analyze a single star's spectrum, splitting its light into wavelengths, you see absorption lines. Dark bands where specific elements absorbed light. Those lines tell you temperature, how hot the star's surface is, composition, which elements it contains and how much, motion, whether it's moving toward or away from us, age, metal-poor stars are old, enriched stars are young. Metals in astronomy means everything heavier than hydrogen and helium. The first stars had almost no metals. They formed from primordial gas. Later generations formed from gas enriched by supernovae, dead stars that synthesized heavy elements and scattered them into space. The very first stars, called Population 3, were massive, metal-free, and short-lived. They exploded within a few million years, seeding the universe with the first heavy elements. We've never seen a Population 3 star. They're all dead. Or at least, we think they are. But what if some survived in binary systems, fed by a companion? What if some are still out there, hiding in the early universe? Eärendil might be one. Or it might be something close. A very early star with just a trace of metals. To know, we needed better data. We needed JWST. Before we get to what JWST found, let's talk about the name. Eärendil. Old English. Eärendil. It appears in an 11th century religious poem referring to the morning star, probably Venus, or metaphorically, John the Baptist heralding Christ. But the word is older, Proto-Germanic. Some linguists trace it to roots meaning shining or ray of light. And if you're a Tolkien fan, you've heard this before. In Tolkien's mythology, Eärendil the mariner sailed to the Undying Lands carrying a silmaril, a jewel containing the light of the two trees that lit the world before the sun and moon existed. The Valar set him in the sky as a star, the morning and evening star, a sign of hope. Tolkien was a philologist. He loved Old English. When he encountered Eärendil in that ancient poem, it inspired his entire legendarium. The astronomers who discovered this star knew the reference. They chose the name deliberately. A star from the dawn of time. A light from before the modern universe. A beacon. Eärendil. Science is full of dry catalog numbers. WHL 0137-ZD1. MAC SJ 1149. Lensed star 1. But the objects we name poetically, those are the ones that lodge in memory. Horsehead Nebula, Pillars of Creation, Sombrero Galaxy. Eärendil isn't just a catalogue entry. It's a story. A connection between ancient poetry and cutting-edge astrophysics. And that story is part of why this discovery matters. Not just scientifically, but culturally. We're not just finding stars. We're reaching into myth. Hubble found Eärendil. But Hubble works mostly in visible and ultraviolet light. For a star 12.9 billion light-years away, Its light has been redshifted, stretched by cosmic expansion into infrared wavelengths. Hubble could see it, barely. But to analyze its spectrum, to understand what it's made of, you need infrared sensitivity. That's JWST's domain. December 2022. JWST pointed its near-spec instrument at Eärendel. 4 hours of integration time, collecting every photon it could. The result? A detailed infrared spectrum. And immediately, things got interesting. Hydrogen, helium, as expected for an early star. But also, faint traces of heavier elements. Carbon, oxygen, silicon. Not much, maybe 1/50th the metal content of the Sun. But not zero. This means Eärendil isn't a true population 3 star. Those would have virtually no metals. It's population 2, an early generation, but not the first. Still ancient, still massive, but not pristine. The spectrum also revealed temperature, around 20,000 Kelvin. That makes it a B-type star, hot, blue, massive. Estimated mass, 50 to 100 times the Sun. Stars this massive burn fast. Lifespan, a few million years. The universe is 13.8 billion years old. Eärendil's light left when it was 900 million years old. That means we're seeing it very early in its life, possibly only a million years after it formed. We caught it in its infancy. But there's a puzzle. Even accounting for gravitational lensing, Eärendil is brighter than expected for a single star. Magnification estimates, 2,000 to 10,000 times, depending on exact alignment. But the observed brightness suggests it might be 2 stars. Most massive stars aren't alone. They form in binary or triple systems, siblings born from the same gas cloud orbiting each other. If Eärendil is a binary, 2 massive stars close together, their combined light would explain the brightness. JWST's spectrum fits slightly better if you assume a binary. 1 very massive star, 80 solar masses, plus a companion, 50 solar masses. Not confirmed, but plausible. If true, this tells us something important about star formation in the early universe. Binary systems are common today. About half of all stars are in multiples. But we didn't know if that was true 12.9 billion years ago. Eärendil suggests it was. The early universe wasn't that different. Stars still formed in clusters. Siblings still orbited each other. Even at cosmic dawn, some things were familiar. Eärendil wasn't alone. Once astronomers knew what to look for, individual stars brightening behind galaxy clusters, they found more. Icarus, 2018. The first lensed star ever discovered, 9 billion light-years away. Mothra, 2023. In the same galaxy as Eärendil, also behind WHL 0137-08. Possibly even more magnified. Godzilla, 2024. Another lensed star in a different cluster field, named because it's massive and appeared suddenly, like a kaiju emerging from the ocean. Yes, astronomers named a star Godzilla. Sidebar. Astronomy naming conventions are delightfully chaotic. We have a galaxy called Hoag's object because it's weird and we don't know what else to call it. A nebula called Hanny's voorwerp, Dutch for Hanny's thing, because a Dutch schoolteacher discovered it. A quasi-star candidate called the Behemoth. And now, Godzilla. The IAU, International Astronomical Union, approves formal catalog names. But informal nicknames stick, and sometimes they're better. Eärendel, Mothra, Godzilla. These names capture imagination in ways that MSS J1149LS1 never could. Finding multiple lens stars isn't just collecting Pokémon. It's statistically important. One lens star could be a fluke, a lucky alignment. But multiple stars behind different clusters, at different distances, tells us this is a repeatable phenomenon. We can start building a census. How common are massive stars at different epochs? How does metallicity evolve over time? Each lensed star is a data point in cosmic history. And there's another implication. Gravitational lensing is one of the best ways to map dark matter. We can't see dark matter directly, but we can see how it bends light. By studying lensed images, especially caustic transits of stars, we can reconstruct the dark matter distribution in galaxy clusters with incredible precision. Eärendil and Mothra helped refine the dark matter map of WHL 0137-08. The cluster's mass isn't evenly distributed. It has clumps, voids, substructure. Each lensed star is a probe, a flashlight shining through the invisible scaffolding of the universe. We're using stars from the dawn of time to map the structure of space itself. Let's zoom out. Why does finding ancient stars matter? After the Big Bang, the universe was hot, dense, ionized, electrons and protons flying free. 380,000 years later, it cooled enough for atoms to form. The cosmic microwave background was released. The universe became transparent. But then, the Dark Ages. For a few 100 million years, there were no stars, just neutral hydrogen gas, cooling, clumping under gravity. Then, the first stars ignited. Those first stars were massive and hot. Their ultraviolet radiation ionized the hydrogen around them, creating bubbles of ionized gas. Over millions of years, those bubbles grew and merged. By about 1 billion years after the Big Bang, the entire universe was reionized. This is the epoch of reionization, the moment the universe became transparent again, this time permanently. Eärendil formed right at the end of this era. It's a witness to the transition. But we still don't know. What were the first stars really like? Mass, metallicity, lifetimes. How many survived? Or are they all gone? Did they form alone or in clusters? Binaries like Eärendil suggest clusters. How quickly did metals spread? Faster than we thought? Every early star we find, every spectrum we capture, refines the answers. Eärendil is one piece. We need dozens more. Let's sit with the scale for a moment. Eärendil is 12.9 billion light-years away in co-moving distance. But space has been expanding since its light left. If you could freeze the universe today and measure the distance in a straight line, it would be 28 billion light-years. The observable universe is 46.5 billion light-years in radius. Eärendil is more than halfway to the edge. We're singing a single star from an era when the universe was 6% of its current age. Think about the photon that entered your eye when you looked at that Hubble image. That photon left Eärendil's surface 12.9 billion years ago. The universe was smaller, hotter, younger. It traveled through expanding space, redshifting, slowing in cosmic time but never stopping. It passed through galaxy clusters, gas clouds, dark matter halos. Eventually, 12.9 billion years later, it passed through a specific region of warped space-time. the caustic curve near WHL 0137-08. That lens bent its path, focused it, sent it toward Earth. And it landed on Hubble's mirror. Then yours. One photon. One impossible journey. Here's the strange part. Eärendil, as we see it, is 12.9 billion years in the past. That star, the specific configuration of hydrogen fusing into helium, is long gone. If Eärendil was 50 solar masses, it died after a few million years, exploded as a supernova, probably 12.8 billion years ago. Right now, if now has any meaning across cosmic distances, that location contains a black hole, or a neutron star, or just expanding gas. We're not seeing Eärendil as it is. We're seeing its ghost, its light echo from the dawn of time. And that's all we ever see in astronomy. Ghosts and echoes. But they're beautiful ghosts. Humans have always told stories about stars, constellations, myths, gods walking in the sky. For most of history, stars were unreachable, mysteries we could only imagine. Now we can analyze their spectra, calculate their mass, trace their evolution. Science replaced mythology with physics, but the wonder didn't go away. It deepened. Naming this star Eärendil wasn't just a Tolkien reference. It was an acknowledgement. Science and story aren't opposites. They're partners. Tolkien created a mythology about a mariner who became a star, a light of hope in darkness. Astronomers found an actual star from the literal dawn, a light from before structure, before complexity, before us. The poetry makes the science mean something beyond data points. It connects the distant and abstract to the human and emotional. Eärendil represents our reach, not just technological, though gravitational lensing and infrared spectroscopy are triumphs of engineering, but imaginative reach. The audacity to say, I want to see a single star from 900 million years after creation. I want to know what it's made of, and I'm going to figure out how. That's what we do. We reach, we grasp, we see farther, and sometimes the universe gives us a gift, an alignment, a caustic, a window, and we see something impossible. Eärendil won't be the farthest star forever. JWST is still observing. More galaxy clusters, more caustic transits. We'll find stars even older, even more distant. Population 3 stars, the true first generation. If any survived, we'll find them. And beyond JWST, future telescopes. More sensitive, larger mirrors. The extremely large telescope. The Habitable Worlds Observatory. Each generation sees deeper, reaches farther. One day, we might see stars from the first 100 million years. Maybe even the very first stars to ignite. We'll keep looking, keep reaching, because we can't help it. So here's where we are. In 2022, Hubble spotted a flicker, a single star magnified by a cosmic lens from 900 million years after the Big Bang. In 2023, JWST analyzed its spectrum, confirmed it's massive, hot, metal poor, possibly binary. In 2024, we're finding more. Mothra, Godzilla, a growing census of early stars. And all of it started with one photon, 12.9 billion years ago, leaving the surface of a star we would later name after a poem, after a legend, after hope. Look up tonight. If you're somewhere dark, you'll see thousands of stars with your naked eye. Every one of them is in our galaxy. Most are within a few thousand light years. Eärendel is 12.9 billion light years away. You can't see it without the most powerful telescopes humanity has ever built, plus a gravitational lens the size of a galaxy cluster. But it's there. Was there. A star from the morning of time. Eärendel, the morning star, the light of the dawn. We saw it, we studied it, we named it. And somewhere, 28 billion light years away in space, in the distant past in time, a star that burned bright and died billions of years ago, is still sending us light. This is Cosmic Canvas, where we reach for the unreachable. Until next time, keep looking up, keep wondering, and remember, the universe is always bigger, older, and stranger than we imagine.